Hi, in this video we're going to talk about extreme values of functions. So the first thing we're going to look at is a lot of vocabulary. So one important thing is that when we talk about extreme values, or really any kind of values of functions, what we're really talking about there are outputs of the function. So when we're talking about many different kinds of values in the next few sections that we'll look at, we're really talking about outputs of the function. So extreme values are also sometimes called extrema. That's a plural. The singular of that would be extremum. So I tend to use the word extreme value or the phrase extreme value when I talk about things, but occasionally in the textbook or in other things you might see extrema or extremum. So that just means the same thing. Okay, so right here, the first thing that we see here for this vocabulary is what it means to be a maximum value of a function. So f of x has a maximum value f of c, so again that's an output value. If that output, f of c, is greater than or equal to f of x for all values of x in the domain. So essentially what this means is that that output that we're talking about there is at least as big as all the other outputs. So we could think of that kind of informally as saying that this is the highest output. This f of c is the highest output of all the outputs in the entire function. All right, there are a couple of other words that we sometimes use to talk about this maximum value of a function. So this sometimes is also called an absolute maximum value of a function, or I'm just going to write absolute max. Also sometimes called a global max. So anytime you hear any of those words, maximum value, absolute maximum, or global maximum, we're talking about the highest output for the entire function. All right, and then similarly, we have another definition here that's just kind of the opposite direction. So f has a minimum value, f of c, so again that's an output. If that output, f of c, is less than or equal to all the other f of x for all values of x in the domain. So that's saying that this f of c is the lowest output for the entire function. All right, so similarly we also sometimes talk about this as an absolute minimum. I'm just going to abbreviate that min, or a global minimum. So a lot of vocabulary there, but we're just talking about the highest output or the lowest output for the entire function. All right, there are a couple of other vocabulary words in this section which we're going to come back to, but we're going to scroll and look at a couple graphs right now and label some of that stuff on the graph that we've already talked about, and then we'll come back and look at the other vocabulary words as well. Okay, so here we see a couple function graphs, and I intentionally put some kind of interesting sorts of points here on these functions. All right, so for this first function, if I'm looking for a maximum value or an absolute maximum or global maximum, I'm looking for the highest y value anywhere on this function. And this function here, we might notice, has a restricted domain. This one appears to have a domain that goes from -2 to looks like x equals about 4. Right, so we've got an x coordinate around here, -2, and around +4. So this one has a restricted domain. And so when we think about the highest output on the function, we're just looking at the highest output for those points that we see here. And so one of the things that you should notice is you got a high point right here. So we have an absolute maximum, or maximum value of the function, and that appears to be just a little under y equals 4. So I'm going to put here y is about 3.9, and that is occurring at x equals 4. All right, and then the absolute minimum, the lowest point on the graph, we've got one right here. So this point right here would correspond to our absolute minimum. And that appears to be not quite down to -1, maybe about y is maybe negative 0.8 at about x equals 2.5 maybe. We're having to estimate here because I don't really have a function equation for each of these. All right, for the second example that you see here, we also have a restricted domain, but this one's a little bit different with the domain. All right, so this one, the left end of the graph, we've got this arrow here, which would indicate that that end of the graph goes on forever in the same direction that we see right there. I've got this jump break in the middle of the graph here, but it appears that there is a point at that x-coordinate, so that's not really a break in the domain. And then at the right end of the graph, I've got this open circle here at about, looks like x equals 4. And so the domain for this one appears to be -infinity to 4, not including 4. All right, so important differences there about the domain that'll pertain to some of the theorems that we're going to look at later. All right, so when I think about absolute maximum or absolute minimum for this function, I want to look for a highest point on the function. And one thing that's important here is to note what this arrow on the left end of the graph is telling us. That's telling us that that graph continues on the way that we see right there. So that's going to indicate that that graph is going to keep getting higher and higher and higher. So this one actually has no absolute maximum. Okay, and then when I look for a low point on the graph, I might tend to look right around here, but one important thing there is that there's not actually a point right there. So it appears from the graph that when x approaches 2, the y values approach 1, but they don't actually equal 1. And so one thing that that means in terms of real numbers and limits is that those y values can get closer and closer and closer and closer to 1, but they won't ever actually equal 1. So there's no actual y value there, so we actually have no absolute minimum either on this function graph. Okay, let's look at some of the other vocabulary and then we'll come back and label some of that on this graph as well. Okay, so a couple of other vocabulary words here to talk about. Local maximum and local minimum. Okay, so let's look at this definition here. F has a local maximum value, so local maximum value. That's also still an output of the function. And we see that that output is greater than or equal to a bunch of other outputs for all values of x, but this time not in the entire domain, just in some open interval containing x equals c. So essentially what that means is near x equals c. On both sides of x equals c. All right, so this is also still a highest y value or highest output, but not necessarily on the entire graph, just in some neighborhood near x equals c. There's another vocabulary word that we sometimes refer to, local maximum. That's also sometimes called a relative maximum. Relative maximum. All right, and then the parallel definition here, we've got local minimum. So f has a local minimum value, f of c. Again, that's an output value. If f of c is less than or equal to f of x, so that's a lowest output for all values of x, but not necessarily on the entire domain, just in some open interval containing x equals c. So near x equals c. So on some neighborhood of x equals c. And this is also called a relative minimum. Okay, so when we look at the examples that we were looking at, we're going to label on those our local maxima and minima. And I'll do that in a different color here so that we can be sure that we're clear about those. Okay, so when I'm looking for a local maximum or minimum, I am looking for points in a neighborhood around that point. So certainly this absolute minimum that we had here of y is approximately -0.8. That is the lowest y value on the graph, but it is also a lowest y value in some region around that. So this absolute minimum that we have here at y equals negative 0.8 is also a local minimum. Okay, I also have a high point on the graph that's not the highest point on the entire graph, but a high point on the graph that's the highest point in that little region around that point. And so I have over here a local maximum, and that appears to be maybe just a little bit over 2. Y is about maybe 2.1. And that appears to be occurring at approximately x equals 1, maybe a little bit left of x equals 1. All right, I've got another low point on the graph over here, and that's the lowest point in that little neighborhood around there. So just kind of zooming in on that part of the graph, that would be a low point. So there's another local minimum over here. Y is approximately maybe 0.1 or 0.2, and x is maybe about negative 0.7 at that point. All right, and then I have these other points that are highest points in some neighborhood, but one important thing is that the function isn't actually even defined on the other side of that point. So the end points of the function here, these actually technically are also local maxima at this end. Because for all of x values around there, that is the highest output values. There's just no other x values on the other side as well. So this absolute maximum at the one end, at the right end, is also a local maximum. And then also at the left end, I have another local maximum. That's the highest point in that region. And that appears to be at about y is approximately 1.5, and x is approximately negative 2 there. All right, so this function graph, I have 2 local minima and 3 local maxima. Okay, on the other function graph, when I think about high points on the graph, we might look at the left end and the right end of the graph, but the left end keeps going up, so there is no highest point there. The right end also keeps getting closer and closer and closer to what appears to be y equals 3, but without actually touching 3. So what that means is that as close as I might be to 3, maybe 2.999, that I can always find another point that's a little closer to 3. So there is actually no maximum, local maximum at either of those endpoints. However, I do have a local maximum right here at that place where the function breaks. So if I look at, say, an interval of about, say, 1.5 to 2.5 on the x-axis here, and if I just look in some neighborhood there around x equals 2, little neighborhood around x equals 2, and I just look at that part of the graph from about x equals 1.5 to 2.5, you can see that in that little region, that point has the highest y value in that region of the graph. Now there are higher y coordinates at other points, but I have a local maximum here. Y is about 2, and that occurs at about x equals 2. Okay, so one other little graph that I want to draw here that I didn't make a kind of pre-drawn graph, but I just want to think a little bit about one sort of interesting example. Let's just think about a sine function. So if I think about a sine wave, one important thing about this is that there are many, many places where that sine wave hits its maximum value, right? So the maximum value of that sine wave is 1. So that's an absolute maximum. Those are also local maxima. But that hits that maximum value at many, many different x values. So x equals pi over 2, x equals 5 pi over 2, x equals 9 pi over 2. So many, many different x values where that y value of 1 occurs. And then similarly, there are many, many places where the minimum function value occurs. So I also have a minimum value of the function, both a local and an absolute minimum of y equals negative 1, but that occurs many, many different places. 3 pi over 2, 7 pi over 2, and so on. So one important thing that I want to emphasize about that is that it may not be higher than all the other points. It might just be greater than or equal to. Notice these inequalities include the or equal to part. So it could be equal to the highest point on the graph. All right, we're going to look in the next video at a couple more vocabulary words and thinking about how to look for local extrema when we have equations of functions instead of just graphs.